He is in some meeting, so I'm going to do the honors of introducing Shanky, one of our friends from the past at IUCAA. He was a student at IUCAA working with Professor Padmanabhan or Paddy. And then he has had an illustrious journey through Europe. He was a postdoc at ICTP, in Albert Einstein Institute in Potsdam, and then in Portsmouth Institute of Cosmology. Then he came back and joined as a faculty member in ICET Trivandrum, and he moved from there a couple of years back, and he's now a professor at IIT Mumbai. And he works on all kinds of things. Today he will tell you about one of the things that he works on, which are black holes, in particular quantum entanglement and black holes. Shanky, take it away.
Yeah, can everybody hear me? Everybody.
I can hear you.
You can hear me. Okay.
Yeah.
So I hope everybody can see my screen. Yeah, I would like to first thank Shomak and Kandu for inviting me for this online talk at IUCAA. I hope everybody is fine, doing well during this pandemic. So today I'm going to talk about a topic which I've been working on for some time on quantum entanglement. So quantum entanglement as an idea goes many decades, and it has been one of the fundamental structures in quantum mechanics. However, only in the last 2 to 3 decades, it has been realized that entanglement is not just a theoretical tool and has interesting applications in wide variety of physical systems. So what today I will be looking at is one of the systems which is interesting for gravity, which is black holes. And what I will try to impress upon you is that there is a one-to-one correspondence between quantities which we can obtain it from quantum entanglement by real-time entanglement entropy calculation with quantities with black holes like mass, temperature, and entropy. Okay, there is a one-to-one correspondence. I'm not saying there is an exact mapping, but there is a one-to-one correspondence which exists. So that is what I will try to highlight in this talk. So the talk is primarily based on the work done with my PhD students, Mahesh and Santosh. Santosh was a former PhD student with me at ICER, and Mahesh is currently the second year PhD student with me in IIT. Fine. And these are the references, relevant references. So it's based primarily the talk will be based on the 4 references, but most of the one-to-one correspondence which I will be mentioning is from the latest paper which appeared in the archive last month. Fine. So the talk will be broadly divided into 3 parts. In the first part, I will briefly introduce the black hole thermodynamics, and I will discuss what is called the problem of universality. So this word was coined by Carleb in early 2000. So I'll just highlight what does it mean and what is relevant, why it is relevant for the black hole thermodynamics. And in the second part, I will I'll explain the entanglement entropy and its measure by focusing on a simple system of 2 coupled harmonic oscillator. And then I will introduce to one of the scaling symmetries which we found recently and which is applicable to field theories in any dimension. I will highlight that and why it is important to understand the divergent structures of entanglement entropy in field theories. Then I will go to the main part of my talk. I'll put the setup, and then I will then give the key results. So I have, since it's a general talk, I have given very little details, but anybody who can ask questions, I'll give the main details of the calculations. Fine. So first I will discuss the black hole thermodynamics. So it is over the last 50 years, we now know that it is possible to think of a stationary black hole in a way analogous to a box filled with a gas which settles down to a thermal equilibrium state. So we know that in the case of a gas in a box, and we know that it can be described by a handful of state parameters like density, pressure, energy, internal energy. So we can also describe black holes, stationary black holes, with a handful of parameters like mass, charge, and angular momentum. These are the ones which are relevant for black holes. for the black holes in GR. And this is now commonly referred to as the no-hair theorem in GR. Now, like the box of gas that satisfies 4 laws of thermodynamics, black hole parameters also, these parameters also satisfy the 4 laws of black hole mechanics. More precisely, one can have a one-to-one mapping between black hole mechanics to black hole thermodynamics if you identify if I do the following mapping. So we identify the mass of the black hole to the energy of the system, or the internal energy, and the area of the event horizon, or the horizon area, is associated to the entropy, and the surface gravity of the event horizon is associated to the temperature T. Then the equations of black hole mechanics as very similar to the equations of give the physical interpretation as equations of thermodynamics. So, for instance, the first law relates the mass of the black hole, or the variation of the mass of the black hole, to the angular momentum, to the change in the angular momentum, and it is indirectly related to the area or change in the horizon area, which is very similar to the change in the energy, and the work done is related to is related to the entropy of the black hole. So, and the second law states that the area of the event horizon of a black hole is always increasing, or it never decreases. The same thing as we do it in the case of, as we know from the second law of thermodynamics. And the third law, which states that the surface gravity of the horizon can never be reduced to 0 in a finite number of steps, which is exactly the same as what we know from thermodynamics. Fine. So, however, these laws are strictly formal in the classical sense, because and there is no direct physical implications, because of 2 reasons. One is that in the case of a classical black hole, the black hole keeps absorbing continuously, and there is anything which comes close to it will just keep absorbing, and it doesn't have any temperature associated. So temperature of the black hole in the purely classical context, where we treat mass, where we treat the fields, the stress energy tensor of the fields, and the gravity to be classical, then it is 0, the temperature is 0, and the black hole entropy is infinite. However, things change dramatically when we treat the matter fields propagating in a classical background, black hole background, for instance, to be quantum. Then there is a temperature associated to the black hole, and which is referred to as a Hawking temperature, because there is a Hawking radiation which comes in, and then which is basically proportional to h cross. So the Planck's constant. So when h cross goes to 0, as I mentioned in the few seconds ago, when h cross goes to 0, the temperature goes to 0, and this is the Hawking temperature. And similarly, the black hole entropy becomes finite; it's no more infinite. So, and then entropy, the finite entropy is basically when h cross goes to 0 here, it becomes infinite. So it is 1 by LP squared. So it goes to 0. So this is something which now people think that it is true, and although there is no experimental evidence, but we know a lot of calculations in various different ways, in various different methods, have shown that this seems to be true. Fine. So there are 2 striking features which is basically what people are interested in to understand for black holes. First is that it doesn't scale as volume, which we know in the case of ideal gas or most of the systems we know in the terrestrial experiments. We know that they are all entropy goes as proportional to volume. Well, in this case, the entropy doesn't go as a volume; it goes as a horizon area, and of course, it is not extensive. Now, the second thing, which is important, is that the black hole entropy is huge. Actually, it's very large. Now, to understand how large it is, so what I have done is I have basically written down the black hole entropy in the units, and I've compared it with to the entropy of the radiation in the entire universe, visible universe, of the current visible universe, and I've compared it like this. So as you can see, just a couple of 100,000 solar mass size black hole can contain as much information or as much entropy as what the radiation of the entire universe, which is with the visible universe, the observable universe, can have. So, which basically tells you that it is since if you can have one supermassive black hole at the center of any galaxy, that will dominate the entire universe entropy coming from the entire universe radiation. So this is a plot by Egan and Lineweaver, which is basically tells you that the entropy of the universe keeps increasing. So, and this is something which I think it's a puzzle now, because with so many black holes being detected. So it seems to be seeing that there is so the most of the entropy of the black hole is entropy of the universe is dominated by the black holes. So this is what is called the entropy problem of the universe, but we will not get into this. But this is something which is interesting to know, that there is this actually has some relevance to what is happening in the current cosmology or in the astrophysical significance. Okay, so the most of the literature, of course, spent understanding the entropy part of the black hole, and that is basically led to the problem of universality. So what does it mean basically? So what we are trying to look at is how does the black hole entropy fit into the standard view of statistical mechanics, in the sense what are the microstates which will lead to the black hole entropy? Yes. So we still don't know what is it. And another related question which has been there for quite some time now is what are the subleading corrections to the black hole, Bekenstein-Hawking entropy. So the Bekenstein-Hawking entropy we know is basically a semi-classical result. So of course it is not a full quantum theory result. So there should be some corrections which should be there, and so there is always an interest of what are the corrections to it, and there are several approaches to calculate that. Okay. Now the main problem with the universality is that at leading order, many different approaches to the black hole entropy all seems to give you the same S is equal to A by 4 in units of C is equal to H cross equal to G equal to 1. And each of these approaches have many different microscopic degrees of freedom, and all of them lead to the same Bekenstein-Hawking. So hence we don't know what are the true degrees of freedom that are responsible for the black hole entropy. So in other words, if everything is true, then it is either we have no information about it, or we have to identify a way to say which one is actually correct and which one is not actually correct. Okay, so this is what is referred to as the problem of universality. So in the sense, all of them seems to give you A by 4, but then, and each of them have very different fundamental degrees of freedom. How can everything seems to give you the same answer? Okay, so then one has to have. So this is I've highlighted this in this flow diagram. So the left-hand side, which is basically represented in dark, is in black, is basically what we kind of know about the black hole thermodynamics. So we know there is a Bekenstein-Hawking entropy, and we know that from this thermodynamics we can define other quantities like Hawking temperature. We can also have the reason why I mentioned it is because these are the things which we will be interested in to calculate. There is also the Smarr-formula which relates all the entropy, the thermodynamic quantities. So now what we have been doing is to assume, to obtain the black hole entropy, we assume a specific degrees of freedom, which is what I mentioned. There are several degrees of freedom. All of them seems to give you A by 4. So there are many approaches which gives you the same answer. Now the question which we can pose is, which is what we have been working on, is whether the same degrees of freedom can have analogous relations to what we know from thermodynamics or the black hole thermodynamics. Like can we obtain like a Hawking temperature, or we can have some relations like a Smarr-formula relation in the analogous degrees of freedom calculation. So only by looking at black hole entropy we will not be able to solve this problem, because that is not going to give us entire information, because we are just only comparing one quantity. But in principle we need multiple quantities, multiple physical quantities to compare, and that is basically what we have been looking at for the last few years. So what I will try to, in the next 30 minutes or so, I will try to show that quantum entanglement of the field across the degrees of across the horizon can help to break this degeneracy, and in principle help us to figure out that how do we calculate some of these quantities, and whether that will help us in understanding which are the true degrees of freedom of corresponding to the black hole. So that is what I will actually go about. So to do this, what I'm going to now look at is to discuss entanglement and define the quantities which are necessary. So to make things simple and also scale it to field theory, so what I will look at is I will consider a simple coupled harmonic oscillator and use this to understand certain things, and also use this to say why this new symmetry, which I mentioned in the introduction, why it is useful. So to get going, so what I will do is I will just start with the Hamiltonian, which is for the two coupled harmonic oscillators, with M1 and M2 mass M. Both are the same masses. We can make it simple. And both of them also have the same spring constant K0, and they are interacting with the interaction term K1. And we have assumed the interaction term to be positive. It doesn't matter whether K1 is positive or negative, but it just for the sake of it, I assume that K1 is positive. And X1 and X2 are the coordinates of the harmonic oscillator, or in this case, the vast space systems, and P1 and P2 are the corresponding momenta for this. And we'll assume M to be equal to 1 just to make life simple. Okay. So we know, like in the classical mechanics, we know how to solve these equations if we go to normal mode coordinates, and we know exactly how to quantize it. And so we know exactly how to get the wave function for the system. So if you assume the ground state wave function, that is the simplest wave function one can assume, then that I have represented as xi0 of x1, x2. X1 and x2 are the two coordinates. So that will be proportional to this Gaussian function, which I've written down here. Fine. So now one thing which is important to highlight is that this wave function, the total wave function of the system, in this case the coupled harmonic oscillator, can never be written as a product of phi of x1 times chi of x2, because it is just a very complicated function because of x1 plus x2 the whole square and x1 minus x2. So then what does it physically imply? It physically implies that individual harmonic oscillator wave functions has incomplete information about the coupled harmonic oscillator system. So we just by looking at knowing the full eigenstate of the single harmonic oscillator wave function will never give us the complete information about the entire harmonic oscillator. So we need to do something slightly different. And such systems are basically quantum state of the systems are complicated, and that is what is usually referred to as entangled states. So if I didn't have interaction, if I put set interaction K1 is equal to 0, as you can automatically see, it will turn out to be a product state, phi of x1 into xi of x2. If K1 is non-zero, then I will always have a state which is entangled, and that is basically what we want to do. So there are several measures to identify how system is entangled. So one of the most popular approaches is basically what is something called the Von-Neumann entropy or the entanglement entropy. So it quantifies how complicated the quantum state is, and it is given by the Von-Neumann entropy definition, which is minus rho log rho. In this case, the rho is basically what we call it as a trace operation. In this case, it is the operation of tracing over all the harmonic oscillator variables 2. In this case, it is 2. So physically, how do we understand this tracing operation? So let us take the case we want to measure the system, and for some reason we choose, as an experimental, we choose not to have information about oscillator, and we try to get only information about oscillator 1, or the other way around, it doesn't matter. So this operation of integration over all the harmonic oscillator 2 variable xi0 star will automatically tell you that I don't have information about x2, I only have information about x1. There is a small typo, it should be x1 prime. Fine. Okay. So what we have is, so if I do this operation by tracing over the oscillator 2, I will get a reduced density matrix. Then I take a trace rho log rho, I will immediately get an entropy, which is what is defined as an entanglement. Just to highlight, it doesn't matter whether I do integrate over oscillator 1 or integrate over oscillator 2. For any bipartite system like what we have, two systems which is interacting, we can integrate over either one of the systems, and I have the final reduced density matrix is going to be identical. It doesn't matter whatever it is. So it is basically one system which we are integrating over compared to other, and either one of them we can integrate. So it doesn't matter, and we'll get the same answer. So that we can verify. Fine. So we can do this analysis for this simple entanglement for the two coupled harmonic oscillator. So, and this is the plot of the entanglement entropy, which is a trace rho of rho as a function of R. R is basically a dimensionless number, which is a ratio of K0 divided by K0 plus 2K. So the reason this is an interesting quantity because it has a finite value between 0 and 1. So it becomes 0 when K0 is equal to when K1 is infinity, then R will become 0. When K1 is equal to 0, that is when the interaction term is 0, then R will become equal to 1. Okay, so so K1 equal to 0 corresponds to the limit when there is uncoupled, when the two harmonic oscillators are uncoupled, and so K1 equal to infinity is when the interaction is very strong, or the coupling is very strong, and that is when R is equal to 0. So you can see that in the case of R is equal to 1 limit, that is when it's uncoupled, that is K1 equal to 0, entanglement entropy actually turns out to be 0. Exactly 0. And in the strongly coupled limit, that is when K1 is equal to infinity, R is actually 0. And this is basically, so there is two things which I mentioned earlier as well. In the case of uncoupled case, we can always write it as a product of two wave functions, that is phi of x1 into chi of x2. And in that case, with the tracing operation will not give you anything, and the entanglement entropy turns out to be 0. In the other case, when it is strongly coupled case, you will have an entanglement entropy which will be non-zero, and in K1 equal to infinity, it will actually become infinity. Okay, so this is a kind of trivially I mentioned, but what we've recently figured it out is that this entanglement entropy has an infinite degeneracy, and this is what I'm going to highlight it in the next couple of slides, because this is important, because this actually helps us to understand something about even for the entanglement entropy relation to the black holes. Okay, so what we found is the following. So there is a symmetry, there is a scaling symmetry, in which the entanglement entropy is invariant, while the Hamiltonian is not invariant. Okay, so this is the result which we had few years back. Paddy was also there. So where we found that for a simple UV-IR relation in a 1+1 field theory, we were able to show this. That time that we were able to show that there is a mapping. But recently, what we found with our student is that this symmetry can be extended to any field theory in 3+1 dimensions as well. And that is what I think is interesting, because that gives us some new insight. Okay, so what we do is, so to understand this, what we do is the following. So let us just take a simple canonical transformation. So we'll say that the PIs are the original momentum, and PI tildes are the new momentum, and X and XI tildes are the old and the new momentum. So we can rescale it. And the rescaling is given by this expression. And K1, please remember, is the interaction Hamiltonian strength. The K1 is the interaction. So if I do this, then my H, the original Hamiltonian, can be rewritten in this way. And where H tilde is basically a rescaled Hamiltonian, which only depends on a parameter, which is K0 and K1. So although H tilde and H are not H tilde doesn't have the dimensions of Hamiltonian, I'm calling it as a Hamiltonian just to tell that it is rescaled by a finite value. Okay, so now the rescaled Hamiltonian is parameterized by a single parameter lambda, and as I mentioned, it's just a K0 by K. Fine. So to understand what is the difference, I have given here the table of the difference between the Hamiltonian H and H tilde. So the normal modes are different. The energy eigenvalues are of course different. Okay. But the most important thing is the entanglement entropy in the scaled and in the unscaled, the original Hamiltonian and in the new scaled Hamiltonian, they turn out to be the same. The zeta is just a complicated function which is just given by. So what it tells us is that there is a new symmetry for which the entropy is invariant, while the energy or the entanglement or the Hamiltonian is not invariant, is not invariant, and this scaling is actually quite interesting. So to understand this slightly better, so what we can do is we'll say that K0, we scale the K0 or the spring constant by some eta times K0, and K1 by eta times K1. So when we do the scaling, the energy is not going to be invariant. Energy is going to be changing because your coupling strength is changed, as well as the spring constant is changed. So obviously the frequency is changed, as well as the normal mode frequencies will be changed. Everything will be different. So the Hamiltonian is not going to be is not the same. It's going to have different energies or different energy eigenvalues corresponding to the system, while the entanglement entropy is invariant. So this tells us that entropy has a scaling symmetry that the energy of the system does not have, and the entropy cannot distinguish between the infinite number of systems generated by the transformation. Basically, eta is any arbitrary number. Eta is not going to be 0, but it can be any arbitrary number. So, and has infinite number of values. So, entropy can take any, entropy will be same for all values of eta, but the energy is going to be different. So, the energy breaks this degeneracy. Once we fix the energy for this system, then we know exactly, even though entropy will be infinite, but we exactly know what should be the entropy, what should be the energy. Fine. So, to understand what I mean by this infinite degeneracy, I have plotted it again, the same plot of the entanglement entropy versus R. So, it's the same thing. R is given by this expression. Now, just we now going to focus on only on the limit R going to 0, which is basically when the entanglement entropy diverges. Now, in the first time when I said we considered a situation where K1 goes to infinity. So, in that case, when K1 goes to infinity, entropy is diverging from this expression because R is 0. Energy also diverges. So, this is basically what we call it as a UV limit of the theory because it's like a highly strongly coupled system. Now, we can also look at another limit which has been overlooked for most of the time and which is what we find it is interesting. So, this is basically what we call it as a K equal to K going to 0. So, K going to 0 is nothing corresponds to the free particle basically because but we are going to keep the interaction finite, but it will be corresponding to a free particle or the 0 mode. In this limit, also the entropy diverges. Okay, so so what it tells us is that the divergence of the entanglement entropy is not necessarily a ultraviolet limit of the theory or the strong coupling limit of the theory. It can also happen when the energy is fine. So what we have found is that this scaling symmetry, although it looks very simple in the case of harmonic oscillator, we have shown that the scaling symmetry exists for harmonic chains as well as field theory, especially for field theories in black hole spacetimes. We have shown that the scaling symmetry exists, and we can always find, even though there can be an entanglement entropy divergent, but we can always find a regime where it is not corresponding to the UV limit of the theory, but will also correspond to where the energy is fine. So the reason why this is important I will highlight it when I'm discussing with respect to the black holes. So the only thing which I would like to emphasize here is that the entanglement entropy divergence is not necessarily a UV limit, but it corresponds also to a limit where the energy is finite. So this is something which is important. I'll come back to it when I'm discussing about the black holes. So that ends the part of my first part of the talk, where I have basically introduced the black hole thermodynamics, and I've also discussed quantum entanglement. So now, some of you might actually wonder, where is the connection between the two? Where is the connection between the entanglement and the black holes? So to understand this, I have given a cartoon diagram of this a black hole, a star which collapses and to form a black hole. So there is a matter which collapses. This is a space-time diagram. T is the vertical axis and R is the horizontal axis, radial coordinate R. So there is a collapsing matter, and once the collapsing matter collapses and forms a event horizon, then it eventually forms a singularity. And let us assume that this is actually eventually settles into a black hole. Now let's look at the situation. So let us take the case that we look at it before the collapse of the matter. Now, since we can in principle obtain every possible information about the system, for instance, the star, we can in principle obtain everything about it. So the entanglement entropy turns out to be 0. However, after the collapse, we know that there is a black hole formed, and hence the black hole is entropy is present, and which is finite. Now let's look at the observers at infinity. After the collapse, after the black hole is formed, there is an event horizon. Hence, the observer at infinity has no access to information within the event horizon. So hence, so as we have done the tracing operation in the earlier case, this observer will have no information from the region from R is equal to 0 to the event horizon. So in principle, it is like a tracing operation, and we will have a non-zero entropy, and that is what is basically what I'm calling as an entanglement entropy to be non-zero. Okay, so there are two things which is important. So once the black hole forms, the black hole, then there is a black hole entropy, which we know from the Hawking's calculation. There is a finite temperature, and hence there is a finite black hole, and which is large. Now, as I argued here, since there is the event horizon, then there is no access to information between r is equal to 0 to infinity for the observer. So hence there is a lack of information, and that results into an entanglement entropy which should be non-zero. So this is the idea with which the Bombay et al. In 1987 showed that this can possibly the way to understand black hole entropy. So both entropies, the entanglement entropy and the black hole entropy, are associated with the existence of horizon. That is number one. The second thing is that both are pure quantum effects, because entanglement entropy is a purely quantum phenomenon. And as I mentioned earlier, the black hole entropy is finite and is large only because of the fact that h cross is not zero, and it is also, and there are no classical analogs for both. Okay, so now let me just go back and look at the cartoon, the flowchart, which I mentioned it earlier. So what I mentioned, so the left hand side of the flowchart remains the same. So what we are proposing here is that we will look at the quantum entanglement of the quantum fields across the event horizon. We integrate over it, and as I mentioned, the Bombay et al. And then Shreddicky have shown that entropy is proportional to the area, and A is the cutoff, which depends on the cutoff. Now, so this is where it has been stopped. So what we want to do is we want to do slightly more. We want to start quantifying other quantities, which is what we call it as entanglement mechanics. I'll explain what does it mean by in the next slide. So the entanglement mechanics is basically which uses the same techniques as what we did in the case of entanglement entropy, uses the reduced density matrix. And we define a quantity called entanglement energy. And we also define a quantity called an entanglement temperature. So, and then what we now show is that is there a one-to-one correspondence between these quantities and the quantities which we know from black hole physics. So that is what I want to impress upon in the next 20 minutes or so. Okay, so now let me just go ahead with the entanglement mechanics definitions. So here again, I've just given a cartoon picture. So this is basically a space-time or a space here. And then I've integrated over a certain region, which is basically region 2. And this is, I'm assuming that we are having a quantum field in the entire region. And I'm going to look at it as a spherical surface, which is integrated over. And then we are going to calculate the reduced density matrix, which is given by this. Now, as I mentioned, the quantifying tool for entanglement or the entangled system is not unique. Entanglement entropy is one quantity which is used. Even in entanglement entropy, even Voigt-Norman is not a unique definition. There is also a Rene entropy and other entropy definitions which are possible. But we will stick to the fact that entanglement Voigt-Norman entropy is the entropy, and we will keep that as a fix it as a definition for entropy. And as I mentioned, the reduced density matrix is a reduced density matrix by integrating over the region 2 here. It can be anything, either 1 or 2, but I have just fixed it as 2. So similarly, we want to define a quantity called an entanglement energy. Of course, there is no unique definition. So what we are defining here is basically the following. So we know that the Hamiltonian has 2 parts. One is basically the Hamiltonian of 1, Hamiltonian of 2, and then there is an interaction. So what we will do is, since we are integrating over the Hamiltonian part 2, so we will multiply the Hamiltonian part 2 and multiply with the reduced density matrix. This is the normal mode operation. Multiply with the reduced density matrix which we have evaluated, and then calculate the expectation value and integrate over all the regions within that region. Okay. So there is a much more fundamental definition which I have not used it, but this is more than sufficient, because this is more than sufficient for the rest of the calculation, for the rest of the talk. So to highlight it, what we are doing is we are only taking the Hamiltonian in the region 2, and we are multiplying with the reduced density matrix which we evaluated over region 2, and then integrating over this region to evaluate the total energy, which is content. Basically, it's like an energy content within that region because of the interaction. Now, of course, as I mentioned, there is no unique definition. Even epsilon is ambiguous. So for the present, we will keep the epsilon to be 1, but we will later on fix that this epsilon can be fixed with a specific value by comparing with black hole parameters. Now, the next thing is we have defined entropy, we have defined energy. So now the next step is to define the temperature. So like in the microcanonical ensemble in statistical mechanics, we define the entanglement temperature to be dE by ds. Okay. So please remember, I've always said K be equal to 1, but that is, we can fix it later. Okay. So basically we have defined three quantities. S entanglement is basically what is used in the literature. So we have just kept that definition as to be the same. So we have defined one quantity which is called the entanglement energy, and the other one is the entanglement temperature. So this might look very artificial right now, but as I mentioned to you, as I show you the results, this actually has an important feature with respect to black holes. Hence, we are using this. Okay, so now to understand the implications of this entanglement energy and entanglement temperature, so what I will do is I will plot it for the coupled harmonic oscillator, and as I mentioned earlier, I will set epsilon equal to 1. So I have basically plotted entanglement energy with respect to the divided by frequency, which is nothing but omega squared is k0. So I am plotting E by omega as a function of R. Now the temperature by omega, which is omega is again square root of k0 as a function of R. R is basically what I defined earlier, which is k0 divided by k0 plus 2k1. Now, as you can see, this entanglement energy also diverges for R is equal to 0, and it is actually goes to 0 when R is equal to 1. So in that sense, when the system is not entangled, you will have zero energy. What we call it as entanglement energy will be 0. Only if there is entanglement, there will be a resultant energy which will be present, and that will what we call it as entanglement energy. So that entanglement energy will be non-zero only if there is entanglement. And if the entanglement is not present, that is when the interaction is 0 in this case, then the entanglement energy will go to 0. So similarly, we have plotted the entanglement temperature, rescaled entanglement temperature as a function of R. So that is in the blue curve. That is the blue curve here. And this is basically, since we know exactly what is the density matrix, we can always map this density matrix to a thermal density matrix. And this is what is the plot of that. And we can calculate an effective temperature from that. And this is what I call it as T bar. So we are showing that. So this also diverges when when R goes to 0. This the entanglement temperature which we have defined, which is in the blue curve, also diverges, and both of them actually turns out to be 0, goes to 0 when R is equal to 1. That is when the system is uncoupled. So in that sense, the entanglement temperature also seems to have a very nice behavior with respect to the entanglement parameters. So entropy, entanglement energy, as well as the entanglement temperature seems to have a monotonic behavior with respect to R. All of them decay with respect when R goes to will go to 0 when R goes to 1, but they are non-zero when R is not equal to 1, and it is between 0 and 1. Okay. So now what we want to do is we want to now scale this up and do it for entanglement. We want to calculate entanglement mechanics for black holes. So this is where I'm not going to give the details, because details are important, but will give you will get into a lot of nitty-gritty details about how do we evaluate and things like that. So to make it simple, I've just given the broad outline of how we actually went about. So what we do is we consider a massive scalar field in four-dimensional black hole spacetime. Since we are going to do everything in coordinate feature, so we actually have done it in two different coordinate systems. One is called the proper length, which is what the results will be based on this. But we have also done it in another coordinate system called Lemaître, and what that is with Santosh. And what we have shown is that this results in the Lemaître, and what we are showing right now are all of them match. Okay. The only problem with Lemaître is we couldn't do it for asymptotically non-flat spacetimes. We could only do it in asymptotically flat spacetime, but we could do it in this case. We are able to do it for all spacetimes. So, but the results are matching for all of it, for whatever we have done. Okay. So the Hamiltonian of the scalar field is given by this. So we don't have to get into the details, but it depends on what is f of r. So just to highlight, I should mention about this proper length coordinate. This is that f of r dt squared, and rho is given by this expression given by this. In the case of Lemaître, zeta and tau are given by this expression. They're all well-defined quantities, and they have interesting implications for different coordinate systems. Okay, So now the important thing is that we can always, as I mentioned in the earlier part, we can always separate this Hamiltonian into scale dependent and the scale independent part. And we will do all the calculations with the scale independent part, because that is will give you all the results, and then we can put it back into the original expression, and we'll get all the answers expressions for the scale scale dependent calculation. So in all the scale independent part and the scale dependent part, the entropy is going to be the same, but all other quantities will be different. Okay, so this is important to as I mentioned in the earlier case. That's fine. So how are we going to do it? We are going to integrate over. I'm just going to show this as a picture. So region 2 is basically the one which contains the horizon, and region 1 is basically outside the horizon. So we are going to integrate over from RH to infinity, and we obtain the reduced density matrix. And we cannot evaluate this analytically, so we need to discretize the Hamiltonian. And since these are spherically symmetric, as I mentioned, this is written in terms of YLMs, polar spherical polar this thing. So we can write the total entanglement entropy in terms of normal SLs, and sum over from L is equal to 0 to infinity. And this is the degeneracy. Okay. So since we are going to numerically evaluate it, so of course we cannot go from to all values of L. So we need to put a convergence criteria in evaluation. So we have put a convergence criteria that the entropy for L plus 1 minus entropy of SL, that is L plus 1 minus SL divided by SL, should be less than 10 power minus 5. So this itself will go to L contributing up to 1000 to 2000. And analytically, we can show that for large values of L, the entropy goes as 1 by L cube. So so our convergence is actually very good. Okay, so now I'm going to just list the plots for different black holes, and then I will show the results, and then we will unify the results in the next after a few slides. So this is the plot of entanglement entropy in the rescaled Hamiltonian with respect to delta H. Delta H is given by RH by A. Similarly, entanglement entropy as a function of delta M, and these are basically different data points. As we keep changing the radius of the horizon, and then we calculate the entropy, and then we plot this. Similarly, we change the radius of the horizon. In this case, is the mass. So we keep changing the mass as like how we change the radius. And then we evaluate the entropy for different values, and then we plot. And each of these are basically different data points. There is a cross which you cannot see, but it is basically a different data points, and all of them seem to give you a reasonably good fit. So once we calculate for the rescaled Hamiltonian, we go back to our original Hamiltonian, and we calculate what is the entanglement entropy for it. So we are assuming epsilon equal to 1, which is important. I'll come back to this, why I'm telling this in the next few slides. So for epsilon equal to 1, we get an entanglement entropy proportional to area, which is what which is known for a long time, and it is proportional to a proportionality constant, which is this is important. I'll come back to this after this. Similarly, the entanglement energy is also proportional to m by a squared, which is important. It doesn't scale as different. It scales as the same as this thing, which is uniqueness for the black hole spacetimes. In the other spacetimes, for instance, in the flat spacetime, it doesn't scale like this. And the proportionality constant turns out to be C. And like how we define the entanglement temperature, we can get an entanglement temperature is given by CE by 4 CSRH. And that we can relate it to the Hawking temperature by given by this. So the T entanglement with respect to the Hawking temperature of the Schwarzschild black hole turns out to be pi CE by CS. CS and CE are the best fit values which we get from the fitting these data points. And this is basically just by taking the differential derivative, and we'll get the answer. Okay, so this is for the Schwarzschild, which is the simplest. Now we did the same calculation for Schwarzschild areas, and given the parameters here. This is the plot of entanglement entropy in the rescaled Hamiltonian with respect to delta H squared. Here, the delta H is a little complicated. It contains parameters of both the mass as well as the cosmological constant. So it is not the, so it is basically RH by A. So similarly here it is entanglement energy with respect to different quantity, which is basically given by 3 delta M minus delta H. Now here again, the entropy scales as area, and the coefficient CS is the same CS which we got in the earlier case. Okay, I will give the value of the CS later on. And the entanglement energy also scales as this 3m minus RH by A squared, and the proportionality constant, which is the fitting function which we get, is the same CE which we get for the Schwarzschild. And when we calculate the entanglement energy temperature, it turns out to be the same as we can calculate this, and it turns out to be exactly the same as pi CE by CS times Hawking temperature. Now we have done the same for Schwarzschild de Sitter event horizon. Similarly, plot event horizon, because the Schwarzschild de Sitter has event horizon as well as a cosmological horizon. We have done it for both event horizon as well as cosmological horizon, but I'm just showing the result for the event horizon. And here again, for the rescaled Hamiltonian as a function of delta B, which is basically the horizon radius. Here again, the energy with respect to this quantity. Now, the interesting thing is the proportionality constant again is the same CS which we got for the Schwarzschild and Schwarzschild anti-de Sitter, CE, which is for the Schwarzschild and anti-de Sitter. And again, we did the same calculation for the entanglement entropy, and it turns out to be the same as what we get for the Hawking, which is pi CE by CS. And so please remember, these are for asymptotic non-flat. Schwarzschild is asymptotically flat. Schwarzschild ADS is asymptotically non-flat. This is also asymptotically non-flat. We have done it even for the Rice-Nordstrom for both the event horizon and the Cauchy horizon. And the proportionality turned out to be similar. So I'm just showing it for the event horizon. And here again, it is the same. The entanglement entropy is proportional to R plus squared by A squared. And the entanglement energy is proportional to the proportionality constant is CE, again is the same. And the temperature turns out to be the same. Okay, so from all this, so I've just shown you this, but we have done it for other spacetimes, but the result turns out to be the same for most of the cases. So now, so once we have these results, so now let us see what are the answers. So what we found is that, so as I mentioned, epsilon equal to 1 is what we have been using. And for all the 4D spherically symmetric black holes, asymptotically flat or asymptotically non-flat, it doesn't matter. CS comes out to be of the order of 0.30 actually. There is numerical inaccuracies in the third decimal place, but that is not really significant right now. But it always comes out to be of the order of 0.13, and C always comes out to be of the order of 0.1. Now the ratio T entanglement by the T Hawking turns out to be 1.26. And this is not just for one black hole, but it is for all the black hole spacetimes. If there are multiple horizons, then for each of these horizons, the answer turns out to be the same. It is not different. So now what we did is we just looked at the correspondence, one-to-one correspondence between the entanglement energy and the entanglement. If I have a black hole entropy, then we can always map the black hole entropy to be 1, but then the scaling relation has an extra factor, CS by pi. Similarly, entanglement energy for all the black holes which we looked at, all of them is with a three-factor CS by A squared. It turns out to be exactly identical to the Komar energy. And the entanglement temperature turns out to be with the proportionality constant, which is pi CE by CS, it turns out to be proportional to Hawking temperature. So the one thing which is important to highlight is that although the entanglement entropy and entanglement energy is sensitive to the cutoff A, entanglement temperature, which we have defined, is independent of A because both of them scale as A squared, so they all cancel out, which is important. So now, so what we did is the following. So since epsilon equal to 1 is arbitrary, so what we did is we said that let us fix by demanding that the entanglement, we fix only one variable, which is basically we fix the entanglement entropy to be exactly identical to the Hawking temperature. So that basically means that we have to fix this constant pi CE by CS is equal to 1, or so we rescale the CE to be CE by 1.26, which is basically the epsilon to be 1.26. So that leads to the universal relation between entanglement energy, entanglement temperature, and entanglement entropy for all the black holes which we have calculated, which is basically E entanglement is 2 times T entanglement times S entanglement. So this is the all quantities which we have derived for massive scalar field propagating in a black hole space. And this seems to be an universal behavior for the entanglement mechanics equation. So now what we found is that this is exactly the same relation as we know for the black hole thermodynamics, from black hole thermodynamics, that energy, Komar energy is exactly equal to 2 times TH into SBH. That is 2 times Hawking temperature times the Bekenstein-Hawking. So So this basically shows there is a one-to-one correspondence. I'm still insisting that it is a correspondence. It's not equality because of the fact that we can get the same relations, but there is a prefactor which is not the same. So in the case of entanglement, we have defined an entanglement energy, and that turns out to be proportional to the Komar energy. And similarly, the entanglement entropy, which is the Weinhausen entropy, turns out to be exactly identical, proportional to the Bekenstein-Hawking entropy. Now, the most crucial is that we fixed it by saying that we wanted to fix the entanglement entropy to be the entanglement temperature to be the same as the Hawking temperature. So that is, which will give you that there is a one exactly identical. So once we fix this, then this relation turns out to be automatically coming without we fudging it. Okay, there is no fudge factor in this because the A is still arbitrary. We have not touched the A. So only thing where we have fixed is the epsilon. Epsilon is an arbitrary function, except that everything else turns out to be the same. So this relation comes out to be, interestingly, the same relation as what we obtain it, what it has been shown how the Komar energy is related to the Hawking temperature and the Bekenstein-Hawking. So this is the one-to-one correspondence which we have got. So what it tells us is that the one-to-one correspondence does not imply equality, because that I wanted to insist, because this will only tell you that there is a mapping which we can do. If I know what is the entanglement energy, we know exactly how to relate it to the Komar energy. But of course, there is a prefactor which we cannot fix it. Now, what we found is that we could also obtain the Smarr-formula of black hole thermodynamics, and which is can be obtained from the entanglement calculation. If I fix that epsilon to be 1.26, then this is how we get the entanglement structure for different black holes, Schwarzschild, Rice-Nordstrom, both for the outer horizon, Schwarzschild ADS and Schwarzschild DS. And if this is what our entanglement structure is, and this is the thermodynamic structure which we know, now what we found is that we were able to derive the Smarr formula, precisely the same expression, which we get from the thermodynamic structure, and which is Smarr formula is a bilinear relation which relates the black hole masses to the other quantities like I'll explain that in a minute. So the this mass, black hole mass, is related to the temperature in this case times the entropy of the black hole. But in the case of Rice-Nordstrom, it is not just the T times Vs, but we also get the Q squared by R squared, which is basically corresponding to the potential. So let me just tell something about the Smarr formula before, and then I'll go back to the table. So we know in the case of GR, the Smarr formula expresses the black hole mass, which is the M, which is what I mentioned, in terms of the geometrical parameters. Like in the case of geometrical parameters, when I mean by the horizon area and the surface gravity, to the dynamical parameters, basically angular momentum, electromagnetic potential, etc. We have not done care, so we don't know much about it, but we can tell precisely that this is true for all the spherical symmetric black holes. So, and the black hole entropy is then identified as a geometric function of the Noether potential. I'll come back to this in a minute. So the Smarr formula is a bilinear relation. It is not a differential relation. It's a bilinear exact relation, which gives you the relation between the mass of the black hole to several of the geometric quantities as well as the potentials. In this case, in the case of Schwarzschild ADS, it actually matches with Trashan et al., who actually obtained the Smarr formula recently for the Schwarzschild ADS as well, for asymptotic ADS spacetimes. We don't know anything about the Smarr formula for the asymptotic DS, but this seems to be consistent with what Trashan et al. Also got. Okay, so one thing which I wanted to highlight is that in all these calculations, all the Smarr formula, including the Komar expressions, they all rely on using the Einstein's equation or the equations of gravity. But in the case of entanglement mechanics, we do not explicitly use the Einstein's equation. We have a fixed space-time background, and we are calculating all the quantum fields propagating on the fixed background, and we are evaluating these quantities. Now, so then the question is, how can these two be equal? The sense this is a question which can be there, because One uses the dynamical equations, the Einstein's equation. The other one is just a fixed background, and we are looking at test scalar fields propagating on it. How can they be equal? So there has been a precedence to this. So there is a well-known relation by Furser and Frollo, who showed in 1998 that Wald, who obtained the Noether charge by using the diffeomorphism invariance of gravity theories, they showed that this is whatever he obtained by looking at the dynamical equations of gravity, also modified theories of gravity, it coincides. This Q coincides with the Noether charge. They obtain it for a non-minimally coupled, again a test, a non-minimally coupled massive scalar field or massless scalar field. It doesn't matter for them. The only importance is the non-minimal coupling propagating in a fixed background. And they showed that this, if they define a Q5, which is basically a difference between two different ways of defining the energy, they showed that this is actually true. So for some reason, so why it works, we don't know. But there is a precedence that whatever we get from the dynamical properties of by using the equations of gravity, the test scalar field, for in this case test quantum fields, or in the case of this test scalar field, seems to have carry that information. Okay, so now why it carries, we have no idea about it, but we think that there is something deep about it, and we are still working on it. So what I wanted to conclude is the following. So what we kind of showed is that we can break the degeneracy in the sense of the problem of universality by constructing other physical quantities, like in this case entanglement energy, and we define something called an entanglement temperature. And if you define this, what we found is that these are independent of the UV cutoff, because the UV cutoff doesn't worry too much. Also because we are looking at the low energies in semi-classical limit, so in principle there should not be any should not have any dependence on the UV cutoff. So we are able to show that the entanglement mechanics has a one-to-one correspondence with the black hole thermodynamics, and we showed that the relation matches with the Komar energy relation, and the entanglement temperature matches with the Hawking temperature. We also showed that the entanglement mechanics relations actually can be identified by fixing one parameter, that is the epsilon, which is equal to some 1.26. It gives out to be equal to the Smarr-formula, which can also lead to, which is a bilinear relation, as I mentioned. Okay, so what I've shown is that there is a one-to-one correspondence, which provides a new way to understand black hole thermodynamics. And this, we can think about whatever we have derived as a third way or independent way to derive the Smarr-formula. Because the Smarr-formula is basically, as I mentioned, is a classical expression which Smarr derived in 1972. And he showed that it's a bilinear expression which we can derive by looking at geometric quantities. Okay. People have derived it in different ways. Now we can think about it. This is a third way of deriving by using everything from the quantum, by using looking at quantum field theory. Now, the one thing which we have shown in the earlier work with Santosh is that the divergence structure of this quantum entanglement mechanics will remain the same even for an interacting theories, because for the interacting theories also the divergence structure remains the same. So we think that the divergence analysis, the divergence structure should remain the same even for an interacting theory. So in that sense, we can in principle extend the analysis not just for the massless scalar field, but also for a lambda 5. So the thing which we are trying to look at is this Frollo-Furser's analysis. Can it shed some light on the Noether charge? How does the entanglement mechanics gives us some information about the Noether charge? That is something which we have no information about. But we are trying to see whether that has an independent way of confirming whatever they have said. So we are also looking at how to extend the entanglement mechanics to higher dimensions, because there is a problem of convergence in higher dimensions, which we are trying to look at. Now, so the question is, if we can extend the entanglement mechanics to higher dimensions, can we get the generalized Smarr-formula also for the higher dimensions? It was obtained by the Barnish and Compre in 2005. They were the first to obtain it for any higher dimension. So we are trying to see whether one can extend it to higher dimensions. Thank you.
Great, thanks. That was a great talk. I'm sorry I missed your initial part of your talk.
Okay.
But this is fantastic. Now I'm going on to the question answer session, which a lot of people here are familiar with. Can I ask everybody, because there's a sizable audience here, to move to the participant window and use the hands up formula to ask questions? You will see a blue hands up thing. So who wants to ask the first question? Are there any questions? Kandu, you start off then.
Shanky, thanks a lot. It was very nice. I was confused in the middle because in calculating this entanglement things, you are integrating from the horizon to the infinity.
Yeah, you can do it either way. It doesn't matter.
Because in the other, when you are introducing this whole thing, you are integrating within region 2.
Yeah, okay. So I should have been I should have been careful the first time actually. So the thing is, what we are doing in all these entanglement calculations, we are sticking to something called a bipartite system. What is a bipartite system? There is a system which is basically like in this picture. This is my complete system, like how we do in microcanonical. This is my entire system, and the system is not interacting with anything else. That's the simplest way of looking at it. And the interaction happens between system 1 and system 2. And the entire outside block is non-interacting, and doesn't exchange energy, something like that, like how we do in microcanonical definition. So it is exactly the same thing. So if I do this, which is the bipartite system, and which is what most of the entanglement calculations are done for a bipartite system, because we don't know anything. There is no unique definition for anything which is tripartite or quadripartite systems or multipartite systems. So only for a bipartite systems, as I mentioned, there is a well-defined way of doing something called a Schmidt decomposition, Gram-Schmidt decomposition, as we know in the usual matrix manipulation. We can do a Schmidt decomposition in this case, and we know that it doesn't matter whether I integrate over 1 or integrate over 2, I will get the same. Entanglement entropy is identical.
Okay, fine. And just one more thing. I mean, when you're calculating it from field theory, you are using some test field.
Scalar field, massive scalar field, yes.
How is it that it's giving you the entropy of the black hole? I mean,
no, it doesn't. So as I mentioned, it is proportional to area. So there is a free constant which is still hanging around, as I mentioned to you. So this is how I relate. So there is an entanglement entropy and there is a black hole entropy. And there is a constant which I have not been able to fix, which is what I mentioned, that I will not be able to fix the constant. And hence there is a correspondence. We don't know the constants completely.
So if you have some n number of fields, will it be multiplied by n?
Yes. Yeah. So very good. So in the case of n fields, this is a problem with the entanglement. So if I have n fields, then it will have n times that contribution will happen. So we have not actually. There is a proposal by several others how to circumvent this issue. But there is no clear understanding of what is the. So there is an n and a. These are two independent parameters in this case.
Right.
How do we fix it? We don't know anything about it. So that's why I said it's a correspondence, but it is not actual equality. So even the energy is also the same in that sense.
Okay. Thanks. Thank you. Thanks.
Thanks. Sriram has his hand up. Sriram, go ahead. I'm unmuting you. Yes.
Hi, Shanky. I was just wondering whether there is any way of attributing a temperature to this entanglement entropy.
So there is a lot of interest in assigning an entanglement temperature by this quantum information guys. So they also try to define various quantities which they use, and one of the quantities is basically how we defined it, as I mentioned to you, as I mentioned here. Yeah. So this is the one way which people have been trying to use even in the quantum information literature. In the sense people use it, we don't know whether it is actually the correct definition. This is just a correspondence. What I want to tell is that we don't know whether this actually will work out. But what I want to emphasize is that if I fix my entanglement entropy to be exactly the same as Bekenstein-Hawking, entanglement temperature as the same as the Hawking temperature, then this Komar relation it will never. Why should this relation should be the same with the factor 2? Why should it be the same as what we get from the Komar relation in black holes? So that is what is important takeaway. Other things are actually not as because we don't know many of the other things, the factors which are there. But why should this entanglement energy proportional is equal to 2 times this is exactly the same as you get as this is surprising. Otherwise, for all black holes we have been able to show this. That is surprising.
Okay. I understand. I have one more question in this entanglement entropy. Have you explored it for something other than spheres? Cubes
yeah,
and
we have done it
cuboids.
for instance, we have done it for a torus. We have done it for other non-compact spaces. Okay. There also the entropy turns out to be proportional to the area. Although the calculations are very much more harder because we cannot even separate.
No, even the Srednicki calculation for a cube or something that has been done.
Cube is done. I think there is a group. There is a group. TU Berlin group, the Technical University Berlin. I think they have done it. They have done it some time back. They have been able to show the calculations and they have been able to get the area for a sphere for a cube. They have been able to show without resorting to spherical symmetry. Yes, they have been able to show.
Okay. Okay, shall we go on to the next one? Naresh has his hand up. Naresh, I'm unmuting you.
Okay. Hello, Shanki.
Hello, Naresh.
Good, nice talk. Now, you said that this, the Barnish and others have done the Smarr-formula in higher dimensions, right?
Yes, that is what I know, but I don't have the complete understanding.
Okay. Now, so what I was wondering is that if they have done in higher dimension, probably one should be also able to do it for say pure Gauss-Bonnet.
Oh yeah, okay, yeah. I think I remember. I think this pure Gauss-Bonnet, not the pure Gauss-Bonnet, but the Einstein plus Gauss-Bonnet. I think this Bibas and all have actually done it, if I remember right. Bibas actually have obtained the generalized Smarr-formula for Gauss-Bonnet. 5D or 6D, I don't know, but I remember seeing Bibas's paper on this.
No, but I suspect, I would say that if you look at the pure Gauss-Bonnet, then yeah, we should get a very simple, decent relation, exactly like the Einstein gravity.
So let me just tell one more thing. Maybe I should have told this before. See, as I mentioned, our analysis doesn't require any knowledge of the gravity theory, right? We don't require any analysis, right? Because we are doing the following. We start with the scalar field and propagating on a fixed background. So the background could have been obtained by GR or for a Gauss-Bonnet or for anything. It doesn't matter.
No, I think that so good. So then I have a question here.
Sure.
That you see, in 7 dimension in pure Gauss-Bonnet, the gravitational potential goes as 1 over r as it in 4 dimensions.
Right. Okay.
And whereas in the 6 dimension it will go as 1 over root r.
Okay.
And so I would suspect that these two relations in the 6 and 7 dimension, you should get a different situation. So I would say in 7 dimensions, in the potential is same as the Schwarzschild, you should get exactly the same thing.
Yeah, but I think the problem with the analysis which we have done extending it to higher dimension is because the convergence criteria will not work. So I'll just explain it slightly so that then I know what I'm saying. So this is what happens, right? This is 2L plus 1. Of course, it will change in the case of higher dimensions. That is not the issue. But the SL doesn't converge as 1 by L cube. Actually, it doesn't converge as 1 by L cube. It actually converges as 1 over L. So I have to account for all values of L in higher dimensions, in 5 dimensions and above. So this is a bigger issue. We have solved it slightly differently in an earlier paper with Brownstein. But
I suspect in 7
yeah, we don't know how to do this currently for the entanglement energy.
No, I mean for pure Gauss-Bonnet in 7 dimension.
Okay.
As well will converge as 1 over L cube.
No. The convergence is more of a problem for us of a computational issue, not as a. There is no physics issue of actually calculating it.
Okay.
It is more of a computational issue, a mathematical problem, than actually as a physical problem. We can in principle compute, but our results may not be trustworthy because we cannot trust these convergence criteria. Because we don't know whether it's more of a mathematical problem. I don't think so. It's more of a physics issue in our case.
Oh, I understand.
Hi, Shanki, this is Sukant. Can you hear me?
Yeah, Shukant, yeah, I can hear you.
Okay, yeah, I was wondering, did you consider applying this method to dynamical spacetimes? Of course, people use tricks like ADF CFT to compute the entanglement entropy.
Yeah, dynamical spacetimes, we have not actually done it. So with the earlier student of mine, we did everything in Lemaître, which is a time-dependent, explicitly time-dependent background. So that's a horrendous exercise to do. We can in principle do it. We have to do evaluate. So the energy is ill-defined. So we have to do other things to define the energy. But we have defined it, and we could actually do it for in a different coordinate system. See, finally, it's about the coordinate system, right? Because I've chosen a coordinate system here, which is time independent. But if I do what I said about the Lemaître, which is explicitly time dependent, I will have a system. I'll have equations. Everything is time dependent. So but I have not done an explicitly like, for instance, Sultana-Dyer, right? Sultana-Dyer is an explicitly time dependent Schwarzschild. We have not done that because the current methods will not work. So we have to come up with something slightly different, because the energy definition is also ill-defined there. So but for instance, for Schwarzschild, Weissenhorst-Sturm, and this where there is asymptotic flat, then we have been able to do it for a time-dependent coordinates, and we are able to get the answer for that. But not in like explicitly time-dependent, we are not able to get it. I don't think so. We are in the current, our techniques will not work for that, because the energy definition becomes very complicated.
I see. Yeah, that's a bit disheartening, but I hope you can find something to tackle that, because then the whole world of things like page curve, etc., become accessible to you.
Okay, the page curve, we have been able to understand part of it because what we did in the case of Schwarzschild ADS, we could get some analysis, but not because again we are only doing it in adiabatic limit, so we will not be able to do the page curve analysis completely in that sense. So even the Lemaître, we could actually go up to page curve, but after page curve is the problem. See, if you are interested in asking a question, what happens after the page curve, it becomes, we were able to go till the page curve peak, the peak of the page time, that what is called the page time, but we were not been able to do anything beyond the page time, because that's where things become more interesting. And that's where all the analysis will fail. Whatever we are doing fails because I don't think so the adiabatic analysis approximation will work in beyond page time.
I hope you find a way to.
Okay, yeah, okay, fine, thanks.
Thanks.
Shomak is muted. Shomak, you're muted.
Great, thanks very much. I don't see any other questions coming up, and unless anybody else does, thank you very much for a wonderful talk and a great discussion afterwards.
Thanks, Shomak.
Thank you very much from us.
Thank you, Shanki.
Thanks.